It's the classic machining conundrum. How do you drill a square hole? Well, with a square drill, of course. A square hole. Well, nearly. The tool skipped a little here as it entered the work, probably due to the surface being a bit rough. A small chamfer might have helped. After a light clean-up pass, it looks a lot better. A nice square hole with sharp internal corners. So what's really going on here? As you probably guessed, this isn't actually a drill. It's a broach. No, not that kind of broach. A broach is a tool used to cut specific shapes by being either pushed or pulled through the material being cut. This is a keyway broach. It works by having multiple teeth increasing in size which progressively cut a slot through the workpiece. Each tooth only takes a small cut, which means the force needed to cut the slot is shared between them. The rotary broach only has a single tooth, made up in this case of 4 edges. If you were to try and push this straight through a round hole, it would most likely just break. The secret is that it doesn't rotate in line with the axis of the hole. It's tilted sideways by a small amount, 1 degree in this case. This tilt causes it to wobble from side to side relative to the workpiece as they spin together. Here the angle has been greatly exaggerated. It's hard to see the wobble with both parts rotating. But if we look at the motion of the cutter relative to the workpiece, the wobble becomes much more apparent. This motion ensures only a small part of the cutting edge makes contact at any one time, thereby greatly reducing the force needed to push the broach through the part. A good analogy is trying to dig hard ground with a spade. If you just try to push the spade straight down, it doesn't work. But if you wiggle as you push, it makes it much easier. Again, rather than trying to force the whole edge into the ground at once, pressure is only being applied along a small section at any one time, concentrating all the effort onto a singular point. This also explains why you can pop a balloon with a pin, but not a potato. This is why a rotary broach is also sometimes called a wobble broach, or even a wabble broach. Wabble being a 17th century English word meaning wobble. It's actually quite easy to build one of these. I made this one from parts and materials I had already. There are really only 2 important things to note. Firstly, the end of the cutting bit must align with the point where the axis of the hole and the axis of the tool intersect. So the length of the cutter is important. Too long or short, and it won't be centered, which could lead to some interesting but unplanned results. And secondly, the relief angle on the sides of the cutter has to be greater than the angle of the tool itself to ensure there is clearance. I used 2 degrees in this case. These are the parts I started with. I decided to make the main body of the tool from 2 steel bars welded together. I could have turned it all out of a single large bar, but that would mean removing a lot of material. Afterwards, I heated it in a kiln to relieve any stress in the steel and get rid of any hard spots caused by the welding. Now I need to bore out the recess for the bearings. I'm using a pair of radial bearings and one thrust bearing, two 6202s and one 51103. I chose these as they can easily handle the forces involved, are a convenient size to work with, and I already had them anyway. The recess needs to be at an angle of 1 degree. I set this accurately using an indicator on the top face of the part. Then I centered the X and Y axes on the part. But I don't want to start boring the hole in the center. If I did, then the end of the tool wouldn't be on the center line. So using trigonometry, I calculate what the offset should be. And move the table over to compensate. That's the exciting mathematics out of the way. Now for the boring part. I'm boring the diameters from the bottom to the top, so I can measure each one more accurately. First is a 30mm diameter for the thrust bearing, 41mm deep. I want this to be a light press fit, so I'm aiming for just under 30mm. The next step up is bored larger to give some clearance for the rotating race of the thrust bearing. This diameter isn't critical. And the final largest diameter is 35mm for the 6202 bearings. Again, I want this to be a light press fit. .99 will do. With the recesses bored, I can go back to the lathe and turn the taper on the tool to suit my tailstock. This is a number 2 Morse taper. I set the angle of the top slide first using an existing taper and a dial indicator. The next part I'm making is the holder for the cutting bit. I'll want to use various cutters, so they need to be interchangeable. This centre on the end isn't just for support in the lathe. You'll see why it's there in a minute. The ID of the two radial bearings is 15 mm, and I need this to be a close fit inside. The cutting bit is secured in place with a grub screw. I made this square cutter from silver steel, which is easy to machine in a soft state, and can then be hardened. The sides have 2 degrees of relief, and I turned a small amount of rake on the end, so it's not just flat. Don't worry, I'll do a final grind on these corners after hardening. You'll notice the hole in the thrust bearing I used is bigger than the holes in the 2 radial bearings. This is a problem, since once the tool holder has passed through the radial bearings, it's too small in diameter to make contact with the thrust bearing. Now, I could have just used a smaller thrust bearing. A 51-100 would have done, and is still rated for around 900 kilograms of force, which should be plenty. But to get the correct minimum abutment dimensions, I would also have to increase the size of the radial bearings to at least 6004s and the diameter of the tool holder to 20 mm, and also increase the size of the whole tool to accommodate everything. This seemed a bit much, so I decided to take a different approach. I machined a plug to fit inside the larger thrust bearing. This has a centre in it, and a ball bearing sits between the plug and the tool holder. I didn't want the end of the tool holder just to butt up against the plug, in case there is any relative movement between the two, which could cause wear. The ball will transfer the thrust load and keep everything concentric. The final part to make is this spacer ring, which maintains the spacing of the radial bearings. Now I can assemble everything. First, the stationary race of the thrust bearing is pressed in. Sockets make very good press tools for this sort of thing. A drop of oil, then the rest of the thrust bearing and the plug. The ball bearing, making sure it's centered. Then the first radial bearing. The spacer. And the other bearing. And finally the tool holder. brooch itself is hardened and tempered. And it's ready for use. By changing the cutting bit, I can broach any shape I like. Here's one I made for cutting very small splines. I should maybe mention that before using any type of broach like this, you first need to drill a round pilot hole, at least as big as the smallest diameter across the broach. You can't simply plunge it into solid material. As well as the lathe, I can also use the tool in my milling machine. Here, with the tool spinning and the work held stationary, it's much easier to see the wobbling action. If you'd like to build one of these yourself, I've compiled a series of drawings showing how I did it. You can either use these as is, or adapt the design to suit your own needs. You can download the drawings for free from my Patreon page, no sign up required. Link in the description.